Hello and welcome. My name is Noah Deer, and this is Lesson 13 of the Math 254 Vector Calculus sequence at PCC. Today we're doing double integrals over rectangles. So we're going to be looking for the volume of the space under a surface given by a function in two variables. And before we do that and get into it, we're going to do some review of how we found areas under curves for a function in a single variable. And we're going to build up just like we did in second term calculus, so in integral calculus, how we built up a Riemann sum in order to find the area under a curve. We're going to build up a double Riemann sum in order to find the volume under a surface. Then we're going to look at a midpoint rule for approximating volumes given data, and we're going to look at finding the average value, the average height of a surface given some region. Oops. Come on. There we go. All right. Section 13.1, definite integral review. In single variable integral calculus, the definite integral is defined to be the area between a curve and the horizontal axis. And we can have negative area too, so if we're below the x-axis, then we consider that negative area. And if we wanted to find it as a positive area, we would just negate it and work with it that way. But given a function y equals f of x, the area from x equals a to x equals b under the curve can be found by cutting up the interval a comma b into n subintervals, constructing a rectangle for each subinterval whose width is that of the subinterval and whose height is some y value of the curve within the subinterval. Let's take a look at the graph so we can see what's going on here. So here we have a curve, y equals f of x. We have some interval from 2 to 5, that's my a and my b. And then we cut it up into n subrectangles. And the width of each rectangle is the total width, 5 minus 2 divided by how many rectangles we have. So right now I have 11, so it would be 5 minus 2 is 3 over 11th. 11 is 3/11ths is the width of a rectangle. Then we set the height of each rectangle. Here we're using left end points, so I have the left end point of each rectangle touching the curve, and then we add up the areas of all of these rectangles to get the total area under the curve. And so that looks like 6.0375 here. Oh, so that's the actual area, and this is using an integral in GeoGebra, and here we're doing the rectangles. The sum of their areas is 5.47, so it's a bit of an underestimate there. As we increase the number of rectangles, we see that underestimates should be getting a little bit better. Now we have the sum of my rectangles is 5.805, which is definitely closer to that integral. Let's take this all the way up to 50, and we see that we're only 0.1 beneath now. So that's what we're doing in practice. We're going to use this Riemann sum down here. Let me finish reading this paragraph. Where was I? Then to obtain the exact area under the curve, we take the limit as n goes to infinity. So we're just saying the number of rectangles we want is an infinite number, so that we've constructed an infinite number of rectangles of infinitesimal width. I should be specific here, infinitesimal width, comma, and heights that match every y value of the curve, so that their sum is the area, is the, sorry, I did not have a chance to go through this in detail before reading it. Then to obtain the exact area under the curve, we take the limit as n goes to infinity, so that we have constructed an infinite number of rectangles of infinitesimal width and heights that match every y value of the curve, so that the sum of their areas is the exact area under the curve. This can be done by choosing the widths of the subintervals to be all different and to choose the heights of the rectangles to be any y value within the subinterval of the curve. Let me kind of show you what I'm saying there. Let's drop this number back down. So I could actually make it so that these rectangles weren't of the same width. I could have one that's width is like 1, and one is 1/2, and one is 1/4, and the next one's 1 again, and then one's 3/4, and that's fine. And then the y values don't have to be left end points. They could be midpoints, or they could be 3/4 points, or some of them could be left end points, some could be right. Because as we take the limit as n goes to infinity, it squeezes everything down so that all of the widths go to 0 anyways, and all of the points between. So if I have a rectangle of width 1/2, then I could pick an x value anywhere between 2 and say 2.5 here, and as to plug into my function to get the y value of this rectangle. But as the width goes down, that choice becomes just the single x value of each of the rectangles as their width goes to 0. So whether we're doing left endpoints or right endpoints or midpoints doesn't really matter when we take the limit as n goes to infinity. Where was I? So what I was saying, this can be done by choosing the widths of the subintervals to be all different, and to choose the heights of the rectangles to be any y value within the subinterval on the curve. And moreover, we could find our area with trapezoids instead of rectangles. So there's lots of flexibility in how we can construct these areas. However, a simple way of constructing this is to cut the interval from a to b into n subintervals. A equals x0, comma x1, comma x1 to x2, comma x2 to x3, comma etc., comma x sub n minus 1, comma x sub n, so that we have n subintervals of equal width. Delta x equals b minus a over n, right? So simply making it so that each of the widths is the same. And we can thus find or choose x sub I equals x0 plus delta x times I for I equals 0 to n. So if I is 0, we would just get x0, our left endpoint of the interval. If I is n, we have then multiplied delta x n times and added that to x0, which will give us x sub n. We can then choose the height of the subrectangles for each subinterval to be that of the y value on the curve that is on the left endpoint of the interval, so that the height h sub I equals f of x sub I are the heights of the rectangles 0 through n minus 1. So we're going to not use the n value here if we're doing left endpoints. If we were doing right endpoints, we would choose I equals 1 to n for my x sub I. So the x sub I are the x's that we're plugging into the function to get the y values, the heights of each rectangle. So the area under the curve can in this way be found to be the integral from a to b of f of x dx. This is defined to be the area under the curve of f from a to b. This equals the limit as n goes to infinity of the sum of I equals 0 to n of f of x sub I times delta x. And I totally have a typo. I just said it, and this needs to be n minus 1 if we're doing left endpoints. Taking notes for mistakes to fix for you guys. Where delta x equals b minus a over n, and x sub I equals a plus I times delta x for I equals 0, comma 1, all the way to n minus 1. So let's do an example of this, get it all set up and everything. Find the area under the curve f of x equals 1/2 x plus 3 over the interval from 0 to 4 via the Riemann sum as described above. So we want the integral from 0 to 4 of 1/2 x plus 3 dx. And yes, we could totally use our antiderivative rules in the fundamental theorem of calculus to evaluate this, but we're going to do it using this limit of the rectangles, limit of the area of the rectangles, to rehash the Riemann sum so that we can then apply this for our volumes. So this equals the limit as n goes to infinity of the sum of I equals 0 to n minus 1 of, okay, so f of x is 1/2 x plus 3. So I need 1/2 of x sub I plus 3 times delta x. Now, have x naught equals 0, delta x equals 4 minus 0 over n equals 4 over n. And so x sub I is going to equal 0 plus 4 over n times I. And we'll do from I is 0 to n minus 1 to give us the x values on the left endpoints of our rectangle. So this equals the limit as n goes to infinity. So just think of this as a substitution thing. We have our formula, the sum of I equals 0 to n minus 1 of f of x sub I times delta x, and we just need to plug in now into f x sub I, and we need to plug in for delta x what we come up with for delta x. So the limit as n goes to infinity of the sum of I equals 0 to n minus 1 of 1/2 times 4 over n times I plus 3 times 4 over n. So we'll just go ahead and distribute some stuff across here. I equals 0 to n minus 1 of, when I multiply this in, so I'd have 2 over n times I, but multiply it by this, and we get 8 over n squared times I plus 12 over n. So this equals the limit as n goes to infinity of, so I'm going to do each of these individually. The 8 over n squared, this is actually a constant for the sum, but the n is a variable for the limit. So as far as the sum is concerned, the I is the variable and the n is the constant. N minus 1 is actually a constant. It's the final, it's how many terms we're using. We're using n terms because we start at 0, so 0 to n minus 1 is n terms. And n is some constant that we've chosen. It could be that we've cut it up into 4 rectangles, 6 rectangles, 8 rectangles, what have you. We'll take the limit after taking the sum here. So this is 8 over n squared. And we need to remember that the sum from I equals 0 to n minus 1 of I, this equals n minus 1 times n over 2. So when I take the sum of I over and over again, really this is a constant, so it can be thought of as factoring it out of the sum, and we're just adding the numbers 0 plus 1 plus 2 plus 3 plus 4 plus 5, adding all of those up and then multiplying by 8 over n squared. When we add all of those up, this is what we get, is what however many numbers we're adding to is n minus 1 times n over 2. Plus, now the sum of 12 over n. Well, the sum of any constant is saying that I'm adding this to itself n times. So this is c times n. So the sum of 12 over n is saying we're just adding this. I is not in this, so I is our variable. There's no I, so this is just saying add this constant to itself. Here we're saying add this constant times 0 plus this constant times 1 plus this constant times 2 plus this constant times 3, etc. Here it's just this constant plus this constant plus this constant, and we're doing it n times total, so that's 12 over n times n, which we're going to obviously simplify this. I think I can do this in just a couple more lines here. This is the limit as n goes to infinity of, here I'm going to get, well, let's write this out. This is 8n squared minus 8n over 2n squared plus 12 equals 4 plus 12 equals 16. And I'm getting the 4 here from 8 over 2. The limit as n goes to infinity of this fraction is simply just the ratio of the highest degree terms. So 8 over 2 is 4, plus the 12 sticks around, we get a total of 16. Let's take a look and make sure that that makes sense here. If I was doing this using integration, we would get 1/2 times 1/2 x squared plus 3x from 0 to 4 would equal 1/4 times 16 plus 12 minus 0 when I plug in 0. And sure enough, we get 4 plus 12 equals 16. So we have confirmation here. Great. So that is our quick review of doing Riemann sums with functions in a single variable. And now we will move on to doing it with functions in 2 variables. So hold on to your hats and glasses. We're going to have a lot of little tedious stuff, but we'll get through it. 1 second. All right, section 13.2, volume, double integrals, and Riemann sums. We can now extend this idea to functions of 2 variables to find the volume between the xy plane and a surface given by z equals f of x comma y. Let the region R equals a comma b crossed with c comma d. So this is an x interval and this is a y interval. Represent the set of x comma y such that a is less than or equal to x is less than or equal to b, comma c is less than or equal to y is less than or equal to d. So define f of x comma y on R, this region that we're talking about, this rectangular region, and for the moment assume that f of x comma y is greater than or equal to 0. As we saw with taking the integral or looking for the area under a curve for a function in a single variable, if we had area underneath the curve, we would have it be considered negative area. We will eventually do the same thing here when we're taking the integrals for functions in 2 variables. But for now, as we do this discussion on how we set up the Riemann sum, we want to just assume that everything's above 0 to be able to talk about how it sets up. So we're going to subdivide the x interval from a to b into n subintervals, x0, x1, then x1, x2, all the way down to x sub n minus 1, x sub n. And then we'll take the y interval c comma d, and we're going to cut it into m subintervals, y0 to y1, y1 to y2, etc., all the way down to y sub m minus 1, y sub m. To obtain the rectangles, r sub I comma j equals x sub I comma x sub I plus 1 crossed with y sub j comma y sub j plus 1. So this is a rectangle that we're going to look at here where this point is x sub I, y sub j, and this is x sub I plus 1, y sub j plus 1 in the upper right hand corner. So this is considered rectangle r sub I comma j, and this we have these rectangles for I equals 0, 1, 2, all the way up to n minus 1, and j equals 0, 1, 2, all the way up to m minus 1, so that we're doing lower left end points for these rectangles. We'll see that in the picture here in a few moments. Note that we could construct the rectangles to not be of uniform widths and still have this work out, but for simplicity we will construct them to all have equal widths so that delta x equals b minus a over n, and equal lengths, delta y equals d minus c over m. Remember, n is the number of cuts that we do in the x direction, or it's the number of intervals that we have in the x direction. There's actually one less cut than that. And m is the number of intervals we have in the y direction. So this is going to give n times m rectangles of equal width and length. So let's take a look at this graph now. Here's from a nice view. If I look from the top view, so I've got a region here I'm not seeing my axes. I don't know why it's not showing the axes. It's weird when I try and do this in this small window. But this function set up where x is going from 0 to 3. We have it cut up into 6 subintervals, each of length 1/2. So 1/2, 1, 1.5, 2, 2.5, 3. And there's a wide interval of total of 2. So again, these are cut into widths of 1/2, 1, 1.5, 2. So 4 intervals in the y direction, 6 in the x direction. So this is saying n is 6 and m is 4 as I have it now. So what we can see, what we're going to do here is as we cut up this region into these rectangles, then we can get the volume of each of these prisms here, these rectangular solids, by multiplying their width times their height, or their width times their length times their height, and choosing their height. What we're going to do initially here is use these bottom left endpoints so that the height of this rectangular solid matches, well, really the height of each rectangular solid matches the z value on the surface when looking at the lower left corner of the rectangles that we've cut the region into. And then we can add up the volumes of all of these rectangular solids, and that gives us an approximation to the volume under the surface. And then we can take the limit as the number of rectangles goes to infinity by cutting this into smaller and smaller widths in both the x direction and the y direction. So we can then inscribe a rectangular solid on each subrectangle whose widths and lengths are all delta x and delta y respectively, and whose heights are h sub I comma j equals f of x sub I star comma y sub j star, where the point x sub I star comma y sub j star is any point in the interval x sub I comma x sub I plus 1 crossed with y sub j comma y sub j plus 1. That is that rectangular region. This is r sub I comma j. As long as we're in that rectangular region, we plug any point in that rectangular region into the function to get a height there. And again, like I said, we're going to start by assuming that we choose x sub I star comma y sub j star to equal, let me write this down, 4 lower left corners. We choose x sub I star comma y sub j star to equal x sub I comma y sub j. If we wanted to do, say, lower right corners, we would choose x sub I star comma y sub j star to equal x sub I plus 1 comma y sub j. So we're still doing the lower, but we're now doing the right corners by having x go over to the I plus 1 position. So for sample points x sub I star and y sub j star, we define the double integral over the region R to be the volume of the solid between R and the xy plane, and this should be volume of the solid between R in the xy plane and f of x comma y. So the volume equals the double integral over the region of f of x comma y delta capital A, where A, well, let's say dA equals dx dy. This is the instantaneous change in the area. This is the instantaneous change in x times the instantaneous change in y, so that's the instantaneous change in the area. So here this equals the limit as m comma n goes to infinity. That's the number of subintervals in the x and y direction. So we're making that number go to infinity for both. And we're summing, we have this double sum. We're summing from I equals 0 to n minus 1 and j equals 0 to m minus 1 for f of x sub I star comma y sub j star times delta x times delta y. So this is the width of the rectangle. This is the length. And this is the height. And we're doing this, we're summing over all of the, j is the lengths, and I is the widths. So we're summing over all of these widths and all of the possible x values and all of the possible y values for all of the possible rectangles, right? So, and I mentioned that a second ago, where dA is the infinitesimal area of the rectangles dx, dy. So later in this lesson, we're going to look at choosing x sub I star, y sub j star to be the midpoints of the rectangles, r sub I, comma j. But for now, we will choose x sub I star, comma y sub j star to be the lower left points of each rectangle, so that x sub I star equals x sub I equals x naught plus delta x times I, and y sub j star equals y sub j equals y naught plus delta y times j for I equals 0 through, it should be, well, we can choose 0 through n and j equals 0 through m, but if we want the lower left, we want to make this n minus 1 and this m minus 1. Okay, so we've done a lot of talking theory on how to set this up. Let's put this in practice. Let's look at example 13.2.1. All right, I'm going to try and go slow here. There's a lot of little tedium in algebra that we have to be paying attention to. This first one's not going to be too horrible. Note, I'm having both of these first two be examples. The first one's not too bad. So here we have, let's start with, we want the volume, which equals the double integral over the region, given here. This we could also write as -2, 2 times 1, 6. And here we have 4dA. This equals the limit as m and n go to infinity of the sum of I equals 0 to n minus 1, j equals 0 to m minus 1 of f of x sub I, y sub I, or y sub j rather, times delta x, delta y. So we need expressions for x sub I, y sub j, delta x, delta y, and we need, so my function here, we have f of x sub I, y sub j equals 4, and we have delta x, so the total width of the x is 4, and we're cutting that into n subintervals. Delta y equals, total width is 5, we're cutting that into m subintervals. And so we have the limit as m and n go to infinity of the sum of I equals 0 to n minus 1, the sum from j equals 0 to m minus 1 of 4 times 4 over n times 5 over m. And this is a simple situation where we could find this volume by just recognizing that this is a rectangular solid, which we'll do in a second to confirm. But it's nice to start with a simple example for the purposes of just seeing how to set up this double Riemann sum. So the limit as m and n go to infinity of a double sum I equals 0 to n minus 1, sum from j equals 0 to m minus 1, and this is 2080 over n times m. So we're going to essentially, we think of this as a sum and then a sum of the sum. So this sum is m instances of this happening over and over to itself. So again, the sum, or I'm going to put this, the sum from j equals 0 to m minus 1 of some constant. This equals the constant times m, because from 0 to m minus 1 is m occurrences. I guess I could even write this out. This is c plus c plus c over and over plus c m times equals c times m. So this equals the limit. So m comma n goes to infinity of the sum of I equals 0 to n minus 1 of 80 over n times m. These m's will cancel. And then when we take the sum, well, let's go ahead and write that this equals the limit as m comma n go to infinity of the sum of I equals 0 to n minus 1 of 80 over n. And if I add 80 over n to itself, this is n times, then we're just going to get 80. And now we have no variable left. I mean, this is technically over n times n, but these cancel, and the limit of a constant is just itself. So we get 80. And we can also confirm this because the volume is the width times the length times the height. The width in the x direction is 4. The length in the y direction is 5. The height in the z direction is a constant 4 here. And so we get 5 times 4 is 20, times 4 is 80. So we're confirming that way. Excellent. All right, so before I give an exercise for you to do that has the limits of the summation, let's do one that's where we back off just a little bit and do an approximation to the volume underneath the surface. So example 13.2.2, we're going to find the volume under the surface x plus 2y squared, d capital A, for the region R equals from 0 to 2 in the x direction, 0 to 4 in the y direction. And we're going to use upper right corners for some sample points. We're going to use a delta x of 0.5 and a delta y of 1. So essentially we're not going to take the limit as delta x and delta y go to 0, right? So if we're looking at our example up here, we're actually going to just get the approximation of what the volume of these rectangles are underneath the surface without getting an exact volume. So what we want to do is we want to think, okay, upper right corners, if I have my region R here, let's 0 to 2, in the x direction, and then y naught is 0 and going to y final of 4 here. If I'm using upper right corners, delta x is 0.5, so we're going to cut this into 4 sections, my region R. And delta y is 1, so we're going to cut it into 4 sections this way. So if we're using upper right corners, we want these 16 points here. So we're going to use x sub 1, which equals 0.5, y sub 1, which equals 1. And we can just make our list of points here. So these are the x and y values that we're going to use. So we want then the heights of each of these rectangles. So if I'm looking at this little rectangle here in the bottom left-hand corner, we're using the upper right corner to find its height. So its height is going to be given by 0.5 for x, 1 for y. And plugging this in here, we're going to get 0.5 plus 2 times 1 squared, which equals 2.5. Okay, I'm going to leave x at 0.5, so using x sub 1, and I'm just going to now move through these y values so that we get these for the 4 z values that go at these points here. So I'm going to actually label this z sub 1, 1 instead of z1. So now I'm going to do z sub 1, 2 is 0.5, comma 2, z sub 1, 3, z sub 1, 4, and so we're just moving through the y values here. All of these are going to have the 0.5 for the x value to start, and then we're going to have plus 2 times 2 squared, plus 2 times 3 squared, plus 2 times 4 squared. So we have 8 plus 0.5, 8.5. And we have 9 times 2, 18.5. 16 times 2, 32, plus the 0.5. Okay, so now we've got this first column here, and we want to keep on going now with z sub 2, 1, z sub 2, 2, z sub 2, 3, z sub 2, 4, and x is now 1. So getting into a rhythm where you're seeing the pattern and are able to kind of run through these values quickly is nice. And so we have 1 plus. So if we think about these values, we have 2, 8, 18, 32. And that kind of, we don't need to recalculate these, the parts from the second term with the y in it. Can save us a little bit of time here. And so now I'll do z sub 3, 1, z sub 3, 2, z sub 3, 3, z sub 3, 4. And here we now move to x is 1.5. And so we're now going to take 2, 8, 18, and 32 and add 1.5 to it. So it's just going to be 0.5 bigger than these. 3.5, 9.5, 19.5, and 33.5. And now we just need z sub 4. So this gets a little bit tedious, which is, one reason that we would want to be able to program a computer to just do this calculation for us. But even better is, we're going to be able to start doing some partial antiderivatives that will get us the exact area under the curve. So we're going to get to that here really in the next lesson primarily. In this lesson, we're going to do this approximation first, and then we'll set up the summation and take the limit again in some other situations and get you some practice on that. So now we have 2 for x, 1, 2, 3, 4 for y, and now we're starting to see we can just add 0.5 to these. We can now get 4, 10, 20, and 34. Okay, and so our volume is now going to be approximately the sum of all these z values. So 2.5 plus 8.5 plus 18.5 plus 32.5 plus 19 plus 33 plus 3.5 plus 9.5 plus 19.5 plus 33.5 plus 4 plus 10 plus 20 plus 34. And we need to multiply each of these heights by the area of each of these rectangles. And the area of each rectangle is delta x times delta y, which is 0.5. So now I'm going to add these up. 11, 29 and a half, 30, 62, and 12, 22, 31, 64. And I will bet anything it's 66, yeah, because we are now adding 0.5 to the x values 4 times, so we'll just add 2 to that, 66 plus 68, all times 0.5. So this is, I'm going to multiply the 0.5. So we got 31 plus 32 plus 33 plus 34 equals 63 plus 67. 70 and 60 is 130. There we go. All right, so we now have an approximation to the volume under this curve that volume should be approximately 130 in this region from 0 to 2 in the x direction and 0 to 4 in the y direction. Excuse me. All right, so with that, let's actually make this an exercise for you. See if you can replicate that process that we just went through. So, oops. Go ahead and give this a shot. Pause the video, and I will work through the solution and talk you through it here in just a few moments. Alright, so let's run through this process again. In this one, just to kind of show that we can do this approximation using different corners, we're going to use the upper left corners this time. So here, if I draw my rectangle, my x naught is 0, my x final is 1. Doing a delta x of 0.25, I go x naught is 0, x1 is 0.25, x2 equals 0.5, x sub 3 equals 0.75, x sub 4 equals 1. And since we are using the upper left, we want the left x values from x naught to x3. So we're going to use the first 4 x values we have here. In the y direction, we're going from 0 to 3 with a delta y of 0.5. So y naught is 0, y1 is 0.5, y2 is 1, y3 is 1.5, y sub 4 equals 2, y sub 5 equals 2.5, and y sub 6 equals 3. Since we're using the upper left corners, we want to use the upper y values from y1 to y6, starting at y1 equals 0.5. All right, so my first z value is z sub 0.1 of 0, 0.5. That's going to equal 1.5 after we do our arithmetic, plugging in the 0 for x and the 0.5 for y into x squared minus 2xy plus 3y. We get z sub 0.2 of 0, 1 equals 3, z sub 0.3 of 0, 1.5 equals 4.5, z sub 0.4 of 0, 2 equals 6, z sub 0.5 of 0, 2.5 equals 7.5, z sub 0.6 of 0, 3 equals 9. So that's my first set, and when I add these up, we get 31.5. My next set, moving over to where x is 0.25, and we plug in y's of 0.5, 1, 1.5, 2, 2.5, and 3. Consecutively, we get z sub 1, equals 1.3125, z sub 1, equals 2.5625, z sub 1, equals 3.8125, z sub 1, equals 5.0625, z sub 1, equals 6.3125, z sub 1, equals 7.5625. That's my second set when x is 0.5. Adding up all these values, we get 26.625. My third set of z values we get from moving to x is 0.5 and then going through the y values of 0.5 through 3. Z sub 2, equals 1.25, z sub 3, equals 2.25, z sub 2, equals 3.25, z sub 2, equals 4.25, z sub 2, equals 5.25, z sub 2, equals 6.25. This one was nice. I saw a nice pattern of them just going up by 1. Adding these up, I got 22.5. And then I look at my last column where x is now 0.75, and we put it in the y's from 0.5 through 3. We get z sub 3.1 equals 1.3125, z sub 3.2 equals 2.0625, z sub 3.3 equals 2.8125, z sub 3.4 equals 3.5625, z sub 3.5 equals 4.3125, z sub 3.6 equals 5.0625. Adding up all of these values, we get 19.125. All right. So I then say that my total volume is approximately the sums that I said there, 31.5 plus 26.625 plus 22.5 plus 19.125. Quantity, all of those added up first, times 0.125, which equals 99.75 times 0.125 equals 12.46875. And that 0.125, that is the delta A. Where our delta A is delta x times delta y. And so this is very tedious, right? And that's okay. We want to get a handle on doing the tedium. It will give us an appreciation of what we're doing with the limits. It also gives us a nice understanding of what's really happening here as we get our hands dirty doing this practice. So even though it's tedious, take some pride in doing it and realize that you are learning on how this setup really works, and it's going to inform us more on how we set up the limit and the sigma here in the next problems. All right, and we're making this an example for you, or an exercise for you as well, except for here we're going to find the volume exactly. So this is a now you try. Before you pause the video, I'm just going to show you again. This is an example from a while ago, but example 13.2.1, we want to follow this method here where we're using the double summation with the limit as m and n goes to 0. So if you want to go back to that part of the video and rewatch this and how I set this all up, that can be very helpful. Give it your best shot here, and know that if you're struggling with it, you can always unpause the video and look at what I'm doing. So I will go ahead and work this out and then talk you through it here in just a few minutes. All right, so we're back, and here let's hash this all out. So I'm going to start by noting that delta x is the total width of the x, which is 2, divided by however many intervals we're cutting it up into, which we'll just indicate with the letter n. So x sub I is going to equal 0, the starting value of x, plus delta x times I. This is going to get us this is going to get us left x values starting at 0 when I is 0. Actually the left is going to come when we build the sigma. My bad, I'm going to come back to that in a second. Delta x is 2 over n, so this becomes 2i over n. Delta y equals 3 over m, so y sub j equals 0 plus delta y times j equals 3j over m. Now, if we're using lower left corners when we build up our summation, our volume is going to equal the limit as m and n go to infinity, so that the number of intervals in the x direction and y direction is an infinite number of intervals that are infinitesimally thin. The summation in the I direction, I equals 0 to n minus 1, that will get us the left corner. So when I is 0, we get just x sub 0 is 0, and so on and so forth from there, going all the way up to when I is n minus 1. Right? So if n is the number of intervals, n minus 1 is going to get us the second to last x value. And then same idea for the y direction, j equals 0 to m minus n gets us the lower left corners. And then we want to plug in our x sub I and y sub j into our function f, where our function f is 3x minus 2xy, and multiplied by delta x delta y. So plugging everything in there, plugging in my x sub I is 2i over n, and my y sub j is 3j over m. Into my function f, we get that our volume equals the limit as m and n go to infinity of the sum from I equals 0 to n minus 1, the sum of from j equals 0 to m minus 1 of 3 times x sub I, which is 2i over n, minus 2 times x sub I, 2i over n, and y sub j, 3j over m, close up our parentheses for the function f of x comma y, and multiply by delta x delta y, which is 2 over n and 3 over m. Going ahead and multiplying the 2 over n and 3 over m into the parentheses, and just simplifying this up, we get that this equals the limit as m and n go to infinity of the sum from I equals 0 to n minus 1, and the sum from j equals 0 to m minus 1 of 36I over n squared m minus 72I times j over n squared m squared. So I want to take the sum with respect to j first. We could actually change the order and it will work out the same, but in this case I have it written so that I'm going to do the j first. So I did this off to the side, each of these individually, just to show you some more detail on where I'm getting these answers, but the sum from j equals 0 to m minus 1 of 36I over n squared m, this does not have a j in it, so this is considered a constant as far as this summation is concerned. So we're just adding 36I over n squared m to itself m times. The reason it's m times is because we started at 0 and went to m minus 1. That's actually a total of m terms that are being added together here. So this equals 36I over n squared m times m, which just equals 36I over n squared. Now the sum from j equals 0 to m minus 1 of 72I over n squared m squared times j, this does have a j in it. So the 72I over n squared m squared is a constant as far as this is concerned. It's just the j that is the variable as far as this summation is worried here. So I'm pulling out that 72I over n squared m squared to get that this equals the 72I over n squared m squared times the sum from j equals 0 to m minus 1 of j. Now we use our little formula from way back when for that summation. Where are we? Almost there. Here we go. We had the sum from I equals 0 to n minus 1 of I equals n minus 1 times n over 2. Same thing except for using a j now and m's. Where is my cursor? There we go. Scroll a little bit faster this time. Alright, so the sum from j equals 0 to m minus 1 of j is m minus 1 times m over 2. So just this bit becomes this bit. Note, no sigma here anymore. If you have a sigma here, then you are erroneously putting it there. We have already taken the sum of j to get this. We are not taking a sum again. So this then can simplify. The 72 reduces with the 2 to be a 36. Distribute the m across here, so I get 36 over n squared times m squared minus m over m squared times I. So that I is still there also. Okay, so going back to our volume here, we had that our volume equals a limit from as m and n go to infinity of the sum from I equals 0 to n minus 1, j equals 0 to m minus 1 of 36I over n squared m minus 72I times j over n squared m squared. We've now worked out the sums of the 36I over n squared m to be 36I over n squared, and the sum from j equals 0 to m minus 1 of 72I times j over n squared m squared to be 36 over n squared times m squared minus m over m squared times I. Alright, so this equals, the limit as m and n go to infinity of the sum from I equals 0 to n minus 1 of 36I over n squared minus 36 over n squared times m squared minus m over m squared times I. Now, in this, there is an I in both of these, so I'm actually going to factor that out and recognize that everything else is a constant as far as this summation from I equals 0 to n minus 1 is concerned. So I factor all of that in front. It all still needs to be inside this limit here. We have to do all of our arithmetic inside the limit before taking the limit. We have to finish all of this up before we can take that limit. So I can then just say the sum from I equals 0 to n minus 1 of I is n minus 1 times n over 2. So that got replaced. I also factor out a 36 over n squared from both of these. So I get that this equals the limit as m and n go to infinity of 36 over n squared times 1 minus m squared minus m over m squared times n minus 1 times n over 2. And then reducing and simplifying a bit here, I get that this equals the limit as m and n go to infinity of 18n squared minus 18n over n squared times 1 minus m squared minus m over m squared, closing up our parentheses here. And I got that by reducing the 36 and the 2 and distributing this n across the n minus 1 and multiplying then by that 18 that I got from reducing. And we see now that we can take our limit. Our limit for this first factor here is an n squared over an n squared, so that's going to limit out to just the ratio of the leading coefficients, which is 18. Over here, the m squared over m squared polynomials will limit out to 1, so we get a 1 minus 1 here. So this equals 18 times 1 minus 1, which equals 0. So this has some symmetry to it, right? We're doing the volume under this surface, 3x minus 2xy. And it turns out that part of that volume is above the z equals 0 plane and part of it is below. And the part that is below and the part that's above are the same volume. So the way that the double integral interprets that is volumes that are below the z equals 0 plane are negative. Volumes that are above the z equals 0 plane are positive. In this case, they're being the same. They cancel each other out to give a volume of 0. All right, and that is that problem. Let's see here. Let's go ahead and move on to the next page. We're now going to look at essentially how we can apply this in a little bit more meaningful way now. When I say that, what I mean is if we have measurements that are giving us data points and we want to estimate some measurement that's a computation of those data points, then we're not going to have a continuous function that we can actually take a double integral. We're actually going to have to approximate things by just using the data given. So let's look at this in the following example. Example 13.2.4, a volume of sediment is being measured in a geological survey. The depth of the sediment is measured every 3 meters in both directions and is given in meters in the following table. Use upper left corners to approximate the volume of the sediment. So here we're not able to take a limit as the widths of the rectangles go to 0. Here we have the widths and lengths of each rectangle is 3. We see that delta x equals 3 and delta y equals 3, that there's no adjusting that. So here in the x direction, if we're at the 0, 0 coordinate, if I'm looking down at this, this has a depth of 0. So we move to right in the y direction, we get a depth of 2, 4, 3, then 0 again. And if we moved with y is 0 in the x direction, we would get the depth is 0, 0, 1, 1, 0. So my y values are 0, 3, 6, 9, and 12. My x values are 0, 3, 6, 9, and 12 as well. And the depths, if we have x is 0, when y is 0, the depth is 0. When x is 0 and y is 3, the depth is 2. When x is 0, y is 6, the depth is 4. When x is 0, y is 9, the depth is 3. When x is 0 and y is 12, the depth is 0 again. Now we move to when x is 3. If y is 0, the depth is 0. If y is 3, the depth is 3. If y is 6, the depth is 5. If y is 9, the depth is 4. If y is 12, the depth is 1. Moving to x is 6, then if y is 0, the depth is 1. If y is 3, the depth is 4. If y is 6, the depth is 6. If y is 9, the depth is 5. If y is 12, the depth is 2. Now we go to x is 9. If y is 0, the depth is 1. If y is 3, the depth is 2. If y is 6, the depth is 4. If y is 9, the depth is 3. If y is 12, the depth is 1. Moving to x is 12, last row here, then if y is 0, the depth is 0. If y is 3, the depth is 1. If y is 6, the depth is 3. If y is 9, the depth is 2. If y is 12, the depth is 1. So if we then think our x sub I is going to be starting at 0, and then the delta x is 3 times I, my y sub j is going to be 3 times j, because again y starts at 0. So the volume is approximately no limit now. We're going to take the sum from I equals, we're doing upper left, so I is my x's, we'll do 0 using the left ones, and to n minus 1, note we have 1, 2, 3, 4. So there's a total of 5 x values, but we're going to have 4 rectangles that we use, because there's an interval from 0 to 3, an interval from 3 to 6, an interval from 6 to 9, and an interval from 9 to 12, which makes 4 intervals for 5 given x values. So the first interval is from 0 to 3, the second interval is from 3 to 6, the third interval is from 6 to 9, and the fourth interval is from 9 to 12 in the x direction. We'll have a symmetrical same set of intervals in the y direction here, 4 of them. So I equals 0 to 3 makes a total of 4 intervals in the x direction. And then in the y direction, we're doing from j equals 1 to 3. We want of f of x sub I comma y sub j, and my delta x is 3, my delta y is 3. Now here we're not really able to use this summation because we don't have an expression for my z values, we have a table. So if we're using upper left corners, then my left corners are going to be when x is 0, 3, 6, and 9. My upper is going to be when y is 3, 6, 9, and 12. So we have a total of 16 separate rectangular solids that we're looking at. We have the first one, instead of using a summation, I'm going to essentially just say the area of each, which is 9, actually let's use the delta, the change in area, is 9, and then we have the z values for when x is 0, we're on the left corners, and then y is 3, 6, 9, and 12, we get the z values of 2, 4, 3, and 0. And then when x is 3, we get, and y is 3, 6, 9, and 12, we get the z values of 3 plus 5 plus 4 plus 1. When x is 6 now, y is 3, 6, 9, and 12, we get 4 plus 6 plus 5 plus 2. And then when x is 9 and y is 3, 6, 9, and 12, we get 2 plus 4 plus 3 plus 1. Now really this is 16 different rectangular solids, so we take the area of the base of each and multiply it by each of the heights, but since the area of each base is the same, we've factored it out into the front so that I multiply once instead of multiplying 16 times and then adding. So I have 9 times 2 plus 4 is 6, plus 3 is 9, plus my second one is 8, 4 is 12, plus 1 is 13, and my third one 10, 15, 17, and my fourth row 2 plus 4 is 6, plus 3, I forgot my 1 here, 9, 10, and so here we add these up and I get 9 times 22, 32, 39, 49. 9 times 40 is 360, plus 81 is 441. And so now we have estimated our volume to be 441. Since this is a story problem, I want to write a conclusion and talk about my units here. So the volume of the sediment is about 441 cubic meters. Okay, now that we've done this example, we want to kind of break things up again, but using a midpoint rule. So instead of using lower left corners or upper right corners or lower right corners or something like that, if we have some, so this is my region R sub I comma j, instead of using one of the corners as we have been, we want to use the midpoint right here. So if this is x sub I and this is x sub I plus 1, and this is, well, I guess this is x sub I. Let me specific how I write this. This is x sub I, y sub I, j. This is x sub I plus 1, y sub j. This is x sub I plus 1, comma, y sub j plus 1. And this is x sub I, comma, y sub j plus 1. Then this point here, we're going to call x sub I bar, comma, y sub j bar. And I'll get in, and well, I guess, so x sub I bar is going to be the average of x sub I plus x sub I plus 1 over 2. And y sub j bar is going to equal y sub j plus y sub j plus 1 over 2. And since well, let's see. Okay, so this one, this is going to be y sub j plus 1/2 of delta y. And that is if we're making the change in y equal, so that from y sub j to y sub j plus 1 is delta y, then if I start at y sub j and add half of delta y, I will get to the halfway point between the y values. And similarly, this is going to be x sub I plus 1/2 delta x. And so we're going to see that here. Let me just read this. As seen in the previous examples and exercise, we can formulate our Riemann sum to calculate volume using lower left corners, lower right corners, and upper left corners or upper right corners of the rectangles. Since we are taking the limit as m and n go to infinity, it makes our rectangles infinitesimal, so the y values of the corners collapse on each other. Similarly, we may reformulate the Riemann sum again using the midpoints of the rectangles. So definition 13.3.1, given z equals f of x comma y, the volume between the surface and the xy plane over the region R equals a to b in the x direction and c to d in the y direction, where a to b is divided into n subintervals and c to d is divided into m subintervals, is given by the volume equals the double integral over the region of f of x comma y with respect to capital A, the area, equals the limit as m and n go to infinity of the sum from j equals 1 to m and I equals 1 to n of f of x sub I bar, comma y sub j bar times delta x delta y, where x sub I bar is the midpoint between x sub I minus 1 and x sub I, and y sub j is the midpoint between y sub j minus 1 and y sub j. This method is known as the midpoint rule. So we're going to go ahead and have we're going to break up our x interval into equal parts, equal width subintervals, and our delta y is going to be the same across the y interval. So we're going to break up our y interval into equal width subintervals. And so our delta x is going to be b minus a over n, and our delta y is going to be d minus c over m. So x sub I bar is going to equal x naught plus x sub 1 over 2 plus delta x times I minus 1. So this gives us, if I is, so let's say we've got x naught to x1, then we've got x1 to x2, and we keep going all the way to x sub n minus 1, comma x sub n. Then the midpoint is going to be x naught plus 1/2 delta x. So if I is 1 rather, so my x sub 1 bar is the midpoint between x naught and x1. put that right here. So if I plug in 1 for I get no delta x's, and I just get x0 plus x1 divided by 2, the average of those two. And for x sub 2 bar, this should be the average of x0 plus x1 over 2, the midpoint here, plus a single delta x, so that we move from here over by delta x to get to the midpoint of the next interval, and so on and so forth. So if I is 2, then we are going to add a single delta x to the midpoint of the first interval. If I is 3, we'll add 2 delta x's to the midpoint of the first interval, and so on and so forth. And then similarly for our y midpoints, we will have the average between y0 and y1 over 2 gives me the midpoint for the first y subinterval, and then we add delta y for each successive j value to get to the successive midpoints of each subinterval. So we're going to use this, and we're just going to do an approximation here. Doing the limits and all of that gets really long and tedious here, so we just want to do an approximation for the double integral over the region R equals 0 to 2 in the x direction, 0 to 3 in the y direction of 2x plus 3y squared, delta capital A, with n equals 4 and m equals 3. So if n equals 4, our subintervals in the x direction are going to be 0 to 1/2, 1/2 to 1, 1 to 3/2, and 3/2 to 2, so that we have 4 subintervals. In the y direction, we're cutting up 0 to 3 into 3 parts, so we have 0 to 1, 1 to 2, and 2 to 3. So we have x sub 1 bar equals 1/4, x sub 2 bar equals 3/4. And we see delta x is 1/2, and indeed 1/4 plus 1/2 equals 3/4. X sub 3 bar equals 5/4, and x sub 4 bar equals 7/4. And then my y sub 1 bar equals 1/2, y sub 2 bar equals 3/2, and y sub 3 bar equals 5/2. So we then are going to have all these rectangles. Note, well, let's real quick, I want to say delta x equals 1/2, delta y equals 1. So the double integral over our region of 2x plus 3y squared d capital A, this is approximately going to be, well, the z values of all the rectangles are going to be given by 2x plus 3y squared. And dA is the area of one of the rectangles, let's say. So delta A equals 1/2 times 1 equals 1/2. And then all the z values. So we're going to have, if I plug in, let me write this, f of x comma y equals 2x plus 3y squared. So we want to plug in f of x sub 1 bar comma y sub 1 bar. So that's going to be 2 times 1/4 plus 3 times 1/2 squared, which equals, oops, so 2/4 plus 3/4 is 5/4. It's just lagging here. There we go. So So this is z sub 1 bar. Actually, no, this is z sub 1, 1. We also are going to then do this for f of x1 bar comma y2 bar, which is 2 times 1/4 plus 3 times 3/2 squared. And this equals 1/2 plus 27/4. Oops, I want to write this as 2/4 plus 27/4 is 29/4. I am going to leave that, and I'm going to do this for all three of the y values. So then we have f of x1 bar comma y3 bar is going to be 2/4 plus 3 times 25/4, 75, 79/4. And then we move on to x2 bar, right? We want to do this for all pairs here, x1, y1, x1, y2, x1, y3, and then x2, y1, x2, y2, x2, y3. We see that we have a total of 12 rectangular solids that we're making, right, with all of these, 3 times 4. And so we need to get this for all of these. Now we want to speed this up a little bit, so I'm going to scroll. I want to just kind of get these down. So I've got f of x2 y1 equals, so I'm going to do this a little bit faster. This is 6/4 plus 3/4, and then we'll have f of x2 y2 equals 6/4 plus 27/4, because I'm kind of using what we already did here. F of x sub 2 y sub 3, the 6/4 stays, and then we have 75/4 over here. So now I've got 9/4 plus 33/4 plus 81/4. And then we do f sub x sub 3 bar comma y sub 1 bar. For x sub 3, we've got 5/4 times 2 is 10/4 plus 3/4, and then the next one, x. So I'm just doing my pattern recognition to try and speed up my calculations here. 10/4 plus 27/4 is 37/4. F sub x3 bar y sub 3 bar is going to be 75 plus 10 is 85/4, and then we'll do this for f sub x sub 4 bar y sub 1 bar. So x sub 4 is 7/4 times 2 is 14/4 plus 3/4. And so how did this zoom out a little bit? Let's see if I can fix this. There we go. And then we have f of x sub 4 y sub 2. This is going to be 6 plus 14 is 20/4. I'm just going to leave everything in fourths. F of x sub 4 y sub 3 is going to be 14 plus 75 is 89/4. So I'm going to put all these in now. I've got 13/4 plus 37/4 plus 65/4 plus 17/4 plus 20/4, oops, plus 89/4. And then we want to multiply these by delta A, which is 1/2. So this equals, let's see, all right, so we got 34 and 79 is 113/4. And then I've got 42, 123 over 4 plus 13 and 37, 50, and 65 is 115 over 4 plus 37 and 89. I hate adding 3 and 8. It's 110, 119, 126, 109 here, 119, 126, yeah. 126 over 4, all times 1/2. So that's 236, 336, 346, 351, 451, 471, 477 over 4 times 2 is 8. And we can just leave it just like that, or I can say, okay, 8 goes into 400, how many times? 50 times, and then 8 goes into 64 8 times, so 58. 59 will get us to 172, and then I've got 5/8 left over. And so here we're just using midpoints to approximate the total volume. And so our volume is approximated to be 59 and 5/8. Okay, last topic for the lesson, we want to talk about average values. So section 13.4, average value. Let's build up the idea of average value for the volume between the xy plane and a surface given by z equals f of x comma y on some given domain D. First, let's look at the classic computation for the average of some set of numbers given some set of y values, y1, y2, all the way up to yn. Then the average value is equal to 1 over n times the sum of from I equals 1 to n of the y sub I. Right? That's just y sub 1 plus y sub 2 plus y sub 3 all the way up to plus y sub n, all over the number of objects, right? That's our classic definition for the average value. If we rearrange this equation, we get n times the average value equals the sum of all these elements, right? So if I just multiply the n to the other side, we get that the total sum equals the average times the number of objects, which is a really nice thing to have, to think about it in this kind of backwards way. So writing it in this way is to highlight that the average value is a height y value such that multiplying it by the total number of y values gives us the same as the total of all the y values, right? If I add up all the y values, then if I will get that same total by taking the average value and multiplying it by the number of values. Because we want to extend the average value definition in this manner. So this idea can then be extended that the average value of a continuous function over some interval a to b gives us that the total width of the interval b minus a times the average value equals the integral from a to b of y of x dx. That is the total area under the curve right? This area equals the integral from a, if this is a and this is b, the integral from a to b of y of x dx, where this is y of x is this line here. So that's just all of these heights added together and with infinitesimal widths. That is our area. So we are taking the average of those by saying what's the average height, and the average height is going to be a height where the width times this height is the same as the area under the curve. See how that's a connection to what we were doing here? This total y values divided by the number of them. If I move the n over, then the n is the number of things times the average gives us the total sum. And instead of the number of things, we now have a width. So this is analogous to what we were doing above. We can then say that the average value, and this is what you actually see in our second term calculus, is 1 over b minus a times the integral from a to b of y of x dx. So we can again see that the average y value is the average height, so that the width times this y average gives us the area under the curve. We now extend this to the idea of the average z value of some function z equals f of xy over some domain D, so that the area of the domain, so before we had the width of our interval, now we have the area of the domain times the z average value is going to give us the volume between the xy plane and the z value itself. So the double integral over the domain of f of x comma y d capital A. So we can compute the average z value via the formula. The average z value, let me draw a picture of this. Let's finish reading. The average z value equals 1 over the area of the domain times the double integral over the domain of f of x comma y d capital A. So we've got some surface here over some domain. Let's see. So our domain, say, is circular, but the z values are changing across this. Then, so say we've got my x and my y directions here. Here's my y-axis, and this is parallel to the y-axis. Here's my x-axis. Here's my z. Then the z average is some height where if I multiplied the area of this domain, so this is D, is this space in here. If I take that area and multiply it by this height, then I'm essentially doing a prism volume, not prison, prism volume. So this area times the height of this prism, if we had just a flat top, then we want the area of this prism to equal the area, or I'm sorry, the volume of this prism to be the volume under this curve, right? So we're choosing the z average to be the height where that works out. So let's do that using example 13.4.1, where we're actually doing contour maps, and we're going to use some midpoints to approximate the average value here. Example 13.4.1. The contour map shows the temperature in degrees Fahrenheit at 4 p.m. on February 26, 2007 in Colorado. The state measures 388 miles west to east. So we're going to say that this is my 0. This is at 388. And 276 miles south to north. So we'll say this is the 0 in the y direction. And this is 276 in the y direction. Use the midpoint rule with m equals n equals 4 to estimate the average temperature in Colorado at that time. So what we want to do here is I'm going to start by dividing it down the middle. And I'm doing a pretty rough estimation here. So I want to divide the x direction into 4. I'm cutting it here, cutting it here. And we're cutting it about here, so that I've cut it into fourths in the x direction, so that n is 4. And then I'm going to cut it in the y direction in half, and then in half again, so that I've divided it into fourths. And then we want to look at the midpoints, or approximate midpoints, of each of these. So our map here is showing temperatures, and we can see that the redder the color, the hotter the temperature, the bluer the color, the colder the temperature. Yellow to green is kind of in the middle. And we want to kind of get an idea. Oops, that's not very middle-ish. It's about, sure, there. So we want to know what the z values are for each of these to be the heights. We know that the width here, 388 divided by 4. 388 divided by 4. This equals 97, so this is at 97, and then 194, and then at 291, and then 388, and 276 divided by 4 is 69. So we've got 69, 138, 207, and 69 again would give me 76. Great. So we can see that our delta A is 69 times 97, which equals 6,693. So my volume over the state of Colorado, which is really essentially all the temperatures everywhere added together. So this is my temperature, X and Y, dA. This is approximately all of these midpoint temperatures added up. And then multiplied by delta A. So what do we got here? If we're on, so 28's like the border of the teal and the green. Looks like 32 is right here on this edge. We have something that's out in the middle of the green that's labeled. We have 28 here, 30. Okay, 28 is on the edge of the teal and the green. And then 32 is on the edge of the green and the lighter green to yellow color. So that would say that we're probably about 30 at this point, 32 at this point. Here in this more yellow but slightly green color, that over here says that it looks like about 44 is in the yellow, 44 is on the border of the yellow to that green. If I'm in the middle of that green, it looks like I'm probably about 42. Here we're on that border from green to light, or like the green to greenish yellow, so that's 32. Here if we're in this light blue, we're at like 26, between 28 and 24 here. And so here I'm kind of like on the border, a little bit more green, so that's maybe 27. And we're doing approximations here. Obviously these dots aren't exactly in the center because I'm not using a nice ruler and straight edge here. A little bit tough on a Wacom tablet. So if I want the border of the purple to the green, that's 20. And then the border from the green to the light green, that's, I guess, 24 right there. And then this color is like 42 in here, 42, 42. The yellow is, I feel like this number's wrong, 44 here, 48 there, so the yellow is 46. We're in the yellow. 56 here. If we're in the red, we're probably like 58 because it keeps going up by 4s, right, between these contour lines. This is probably 58. Here we're on this contour line, so 52. Here, 44. 48 and 44. So if I take all these and take this and multiply it by the area, that gives me this kind of total temperature over this region, which doesn't have a whole lot of sense, but when we then divide it by the total area of this region, then we're going to get the average temperature over this region, and that makes a bit, that we can wrap our heads around a little bit better. So let's take these. We've got 30, I'm going to need to have a little bit more room here, 30 plus 32 plus 42 plus 32 plus 24, 20, 27, 26, 42, plus 46, plus 58, plus 52, plus 42, plus 44, plus 48, plus 44. And then we multiply those by our delta A. So we got 62, 104, 136. I'm going to add these 4 at a time. 44, 64, 71, 97, 88, 138, 146, 148, 198, 86, 126, 134, 174, 178. And my delta A is 6,693. This equals 136, and 236 minus 3 is 233. 233 plus 200 is 433, minus 2 is 431, 531, 601, 609. And let's not multiply these together because it's not really what we're looking for. What we're looking for is the average temperature, which is going to be 1 divided by the total area, so the area of Colorado, and times this integral here, the double integral over the state of Colorado of the temperature function with respect to the area. And this then, 1 over the area is 276 times 388. And note that this, so this then, I'm going to kind of just, there's a way that I can simplify this pretty quickly. 6693. Note that this is 4 times 69, and this is 4 times 97. And this is 69 times 97 right here. So this is 4 times 69 times 4 times 97. Let's have a way of canceling things real quick. 609 times 69 times 97. So we can cancel, 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 cancel. This equals 1/16 times 609, which is approximately 38.06. No, that's exactly, but oops. 8.0625. And so we got a story problem here, so we want to write a conclusion and say that the average temperature in Colorado on February 26th, 2007 was about, because this is very much an approximation, we only did 16 points here. If we had, 1,000 data points, we could do this much more accurately. But that would still be an approximation. But this was about 38 point, we'll just say 1 degrees Fahrenheit because, yeah, this was scrolling up here, measured in Fahrenheit degrees. So, and this was at a specific time. So we want to make note of that. This is not over the entire day. This was at a specific time. 2007 at 4 p.m. was about 38.1 degrees Fahrenheit. All right. That's what we have for you in this lesson. Thanks so much for watching, and I will talk to you in the next lesson. Have a